Welcome to lecture 27. In this video, I will cover the pages that are assigned for this lecture, 276 to 283, which generally covers the main thermal events that will occur during exercise, particularly in a hot environment. Let's begin by going over the standard responses to both a heat load and a cold stress, and these are covered in figures 12.4 and 12.5 of your textbook. First, we'll note that the regulatory center for thermoregulation in the body is in the preoptic anterior hypothalamus, and that's the integration center that's shown here and here on these charts. So let's take the top diagram first, and in response to a heat load, we'll see that our thermal receptors, both located in the core and in the skin, will detect now a change in temperature, that is an increase. And then we'll have our effectors, which will include cutaneous vasodilation as well as sweating. The reasons these will be effective is that with dilation, we will get more skin blood flow, which will then enhance both heat loss both by convection and conduction, because we'll be radiating heat out to our cooler tissues near the skin, which then we can lose the heat off to the environment. We will also begin sweating, and of course this will increase our evaporative cooling. Now, going to the lower diagram, we can see the response to a cold stress or a cold environment. Again, we have receptors in the skin and in the core, and our effectors here are going to be several. First off, we will start shivering. That will be conducted by the skeletal muscles, and that will produce some heat. Cutaneous vasoconstriction will do the opposite of dilation. So now we're keeping blood out of the skin where the temperature is cooler. So now blood will be directed more towards the core of the body where it'll stay warmer and will lose less heat to conduction and convection. Catecholamine release and thyroxine release, these two mechanisms will both increase metabolic rate, and so that will also increase your heat production. Now that we've covered these general physiological responses, let's take a look at what happens during exercise. This is in figure 12.6 of your textbook, and this just shows the heat loss mechanisms that have occurred over time, and this will be in a fairly cool environment, and we can tell because the evaporative heat loss reaches a steady state, and so the subject will have reached a steady state temperature. So if we look, this person has been cycling, let's say it could be running, and they have this level of metabolic energy production across or near the top. And then we can look down at the bottom at the convective and radiative heat loss over time. And these are fairly low and they are fairly constant. And that is because the temperature gradient between the body and the environment remains fairly even over this 30-minute exercise bout. However, we can see the increase in the evaporative heat loss as body temperature increases. Of course, we will need to lose more heat, and so we will start sweating, and so this simply reflects our increased evaporation of sweat from the body and that evaporative heat loss until, of course, we've reached this steady state, which occurs over about the last 15 minutes. In the next figure, figure 12.7, we can see that the increase in body temperature or the heat load that's generated during exercise is directly proportional to the exercise intensity, or in this case, along the x-axis, you have the oxygen uptake, or in this case, your VO2. So the bottom line for this figure is that the greater your exercise intensity, the greater your heat load will be, which of course is logical, and then the greater your increase in body temperature is going to be. Next, let's take a look at figure 12.8. This one shows the heat exchange mechanisms at different environmental temperatures. So in this case, we have someone exercising at a constant work rate. Let's say it's 100 watts or 200 watts. And we can see along the x-axis then this will be done in increasing environmental temperature. So about 20 degrees C is about room temperature. It's about 68 or 70 degrees Fahrenheit. So you can see above that, if you get to 25, 30, especially 35 degrees is really hot because we know 37 degrees is body temperature near 98 degrees, right? So let's take a look at the lines on this. First, we have energy output. That's the work that's being done, and that is, or the energy required to do the work, sorry. That's the red line at the top. That's this one here. The blue line shows us the heat production. So the person is producing this much heat. And then the purple and the orange lines are showing us evaporative heat loss is the purple line, and the orange line is the convective and the radiative heat loss. The main take-home point from this figure is that note how the heat loss mechanisms change as the room temperature increases. So first off, at very low temperatures, say down from 5 to 15 degrees Celsius, convective and radiative heat losses are the most important. Why? Because there's a large gradient between body temperature and atmospheric temperature, and we can easily lose heat that way through any of the air currents that might be going over our skin. However, as we reach above 20 degrees Celsius, note that evaporative heat loss is now becoming progressively more important. In fact, there's an interesting point to be made at these high temperatures, the one that's at 37 degrees. Go back to your y-axis and look at the kcals per hour. This is heat exchange, right? Well, at 0, which is here, that would be no heat exchange with the environment. And notice that it's at high temperatures above 35 degrees. We're below the 0. That means the body is gaining heat by convection and radiation. And so, consequently, to maintain a steady body temperature, the evaporative heat loss is now, of course, greater than the actual heat production, because we also have to account for the extra heat that's being gained down here by convection and radiation. Now, the final figure we'll take a look at for this set of reading will be figure 12.9. And it's similar to 12.8, except note that our x-axis here, now it's power output from very low power outputs of 50 watts up to a pretty good workload there of 240 watts. Things to note for this. Obviously, your energy output, that's line number 1, is going to go up progressively because it will be a linear relationship with your workload. Heat production will also go up a fairly linear manner. And then total heat loss is your line number 3 here. Notice that the total heat loss does not keep pace with heat production. So this gap here between heat production and heat loss means that the body has gained heat. So the heat production has exceeded the heat loss, and so the body temperature, of course, will have increased because the body is now storing some heat. It can't dissipate all of the heat that's being produced. The other main takeaway point from this figure is the mechanisms of heat loss. Just like in the previous figure, we saw an increase in evaporative heat loss because as body temperature increases, we should expect greater need for evaporative heat loss. And note that the convective and radiative heat losses, these stay fairly constant. And they do not change much with increasing exercise intensity. This figure is sort of a summary of the last two figures, 12.7 and 12.8. If you recall, going back to figure 12.7, it showed us that the heat load or body temperature increased as a function of power output. And so we would expect, of course, that body temperature will increase as power output goes up, just like in this graph on figure 12.9. So to summarize these last four figures, we now know that as exercise intensity increases and or as the temperature or humidity increases, that the body will have an increased heat load and a challenge for thermoregulation. This will then require greater evaporative heat loss to occur. And we would expect in these conditions, especially if it's hot and humid, that body temperature is going to increase substantially. And so that brings us now to the next section, which is exercise in a hot environment. And indeed, exercise performance is impaired when conditions are either hot and or humid. So moving to my final slide for this video, we can see that performance in a hot environment will be impaired. And this particularly, we're talking about prolonged exercise, say a marathon, a 10K, a triathlon, or something that's high intensity and lasts longer than, say, about 10 minutes. We know that high intensity events that aren't very long in duration will not be inhibited in a hot environment. In fact, it might even be enhanced. Thinking of track sprinters, they love competing in the heat rather than the cold because there's simply no challenge as far as the fatigue mechanisms go in working with a hot environment for these other prolonged events. So let's take a look at the mechanisms of why performance in prolonged events or these high intensity events might be impaired. The first mechanism is an accelerated muscle fatigue. Turns out that in a hot environment, the rate of muscle glycogen breakdown is increased. This causes fatigue mainly in prolonged events because we know glycogen is going to be a main fuel source. And second, if we're increasing muscle glycogen use, that will increase glycolysis and have a higher lactate production, which will then decrease muscle pH. That can also cause fatigue by decreasing force output. And the third mechanism for this, an accelerated muscle fatigue, is the production of free radicals. This ends up being in this book a lot because one of the authors does lots of research on free radicals. But we do know that free radical, these molecules with unpaired electrons, they can also cause a reduction in muscle force. One more related mechanism to muscle fatigue is then the effect it might have also on the central nervous system. If we activate the muscle chemoreceptors, we'll get feedback to the brain that can reduce muscle motor unit recruitment. This would occur over what the book mentions as these type 3 and type 4 afferents. Those are a class of neurons and nerves that are non-myelinated. So they're not as fast as myelinated fibers, but they'll still make their way back to the central nervous system and decrease recruitment of more motor units, which then, of course, will decrease force production. The second major mechanism that reduces performance in a hot environment is cardiovascular dysfunction, and the book also refers to this as cardiovascular strain. And this will occur primarily in very high intensity exercise. The mechanism here is that you will have an increase in heart rate and a decrease in stroke volume that ultimately will decrease muscle blood flow. And obviously, with a lower blood flow, you have lower oxygen delivery, and that will decrease muscle force output. One of the main causes for this will be an increase in the blood flow to the skin for, obviously, thermoregulation. Here we need more blood for radiative and convection heat loss. So as more blood goes to the skin, that means less blood available to go to the muscles. That brings us to the third main mechanism for reduced performance in a hot environment, and that's the central nervous system dysfunction. And basically two mechanisms for this one. As body temperature increases, we experience hyperthermia, and this will reduce our activation of motor units. And so it's sort of a governor, a switch that's turned on, and it reduces our ability to excite motor neurons. It's our body telling us, nope, stop exercising, you're too hot. And the other one, of course, we've already mentioned, the other mechanism here would be the feedback to the brain from these type 3 and type 4 afferents, those chemoreceptors that are in the muscle. That will also reduce muscle activation, reduce force output, and cause us to slow down. That concludes the main points from Lecture 27. Be sure to tune in for Lecture 28, in which I will cover heat acclimation.